Welcome to The Explainer. Today, we're shining a massive spotlight on a hidden electrical threat that can literally destroy a transformer from the inside out. We're talking about faults lurking right near the transformer neutral point. It's a notoriously tricky area to protect, but stick with me because by the end of this session, you're going to know exactly how to secure it. Okay, let's dive right into this. A fault right next to the neutral point produces almost zero differential current imbalance. So from your standard differential relays point of view, it's practically invisible. And that is exactly the blind spot that ground fault protection is built to close. Transformers simply cannot tolerate sustained fault current without rapid thermal runaway and, well, mechanical deformation. Leaving this unprotected creates a massive, highly dangerous vulnerability in your entire protection scheme. To really wrap our heads around why we need a totally separate system for this, think of it like a high-end security setup. People sometimes assume ground fault protection is redundant if you've already got differential protection, since they both watch for current imbalances, but they are solving completely different problems. Differential protection is your wide-angle security camera. It monitors the whole room, tuned for balanced zone phase faults. Ground fault protection? That's your dedicated close-up camera trained directly on the safe in the corner. It zooms in on the one spot most likely to hide a small fault.
And this dedicated close-up camera is what we formally call Restricted Earth Fault Protection, or REF for short. In plain language, an REF scheme basically draws an invisible electrical boundary, like a digital fence, around the transformer winding and its neutral connection. Any earth fault current inside that fence, bam, it trips the relay. Anything outside that fence, it flows right past without tripping it. It gives you true selectivity, completely ignoring external earth faults while offering extreme sensitivity to the internal ones.
Now, when you're setting up an RET615 relay to actually implement this, you've got two fundamentally different technologies wearing that same ref name. And let me tell you, mixing these up at the specification stage is one of the most common causes for commissioning delays in the whole industry. These two distinct solutions are LERFPDIF, which is our low impedance scheme, and HREFPDIF, the high impedance scheme. Let's break down exactly what each of these does.
First up is LRFP-NDF, the low impedance ref. This is a highly flexible, software-driven numerical scheme. What makes this one so appealing is that it's super simple to commission. Why? Because it requires absolutely no external hardware. No stabilizing resistors, no varistors, nothing. It's incredibly clean. It just uses internal numerical algorithms right inside the relay to compensate for equipment variations, specifically when your current transformers, your CTs, don't perfectly match. On the flip side, we have HREF-PDIF, the high impedance refit. This is your old-school traditional method. It relies on a physical high impedance path to provide extreme sensitivity for faults near the neutral point. But that extreme sensitivity comes with some pretty intense hardware constraints. It strictly requires identical CT turns ratios throughout the circuit, and it usually demands external hardware like stabilizing resistors to even function properly. So, it trades that software flexibility for rock-solid physical stability.
Choosing between low and high impedance ref is a lot like choosing between a universal remote and a manufacturer-specific deadbolt. Low impedance ref is that universal remote, right? You can reprogram it through software to adapt to mismatched equipment and completely different systems. High impedance ref is the deadbolt keyed to one exact lock. It demands that every single piece of hardware matches perfectly, but once it does, nothing beats it for keeping that one specific door secure.
So how do you actually choose? Well, the entire decision relies on one immutable rule: verifying CT turns ratios. You absolutely must verify your CT ratios first, every single time. This one piece of data dictates your entire engineering path forward. If you get this wrong, there's no way you'll be able to properly commission the reef scheme. Let's walk through the definitive selection procedure. Step 1. Check the turns ratios between your phase CTs and your neutral earthing CT. Step 2. If those ratios differ, you must use the low impedance scheme, LRFP-NDF. End of debate. Step 3. If the ratios are perfectly identical, well then you have the luxury of choice. You can use either the low impedance scheme or the high impedance HRFP-NDF. Just keep in mind that high impedance will require those external resistors.
Now, what's really interesting about this slide is mapping this directly onto the standard configurations of the RET615 relay. If your application drives you to a low impedance solution, you're going to be looking at configurations A and E for transformers with earthed high voltage neutrals. If you're protecting a solidly earthed low voltage side or an LV side with a neutral earthing resistor, then you'll select configurations B or F.
Conversely, if you're going the high impedance route, you'll look at configuration C and G for the HV side and configurations D and H for the LV side, and take a close look at the explicit requirement highlighted right there on the screen, equal CTs. Ordering configuration C, D, G, or H for a network with mismatched CT ratios is going to leave you completely unable to commission the protection scheme. It's a dead end.
To ground this abstract concept in reality, let's look at a physical setup. Here we have the RET615 applied to a 2-winding power transformer in standard configuration D. Notice the high impedance ref protection applied specifically to the low voltage side. The CTs on the phases and the CT on the neutral must have perfectly matched ratios for this particular physical setup to accurately monitor the protected zone without false tripping.
So you might be wondering, why do we even need that external stabilizing resistor for high impedance to work? Well, it's all about physics. High impedance ref stays stable because it relies on a physical high impedance path. During an external fault, which is outside our invisible boundary, any slight mismatch current caused by minor CT imperfections is physically forced through that stabilizing resistor. And this resistor is often sized in the hundreds to thousands of ohms. The current goes there, instead of flowing through the sensitive relay operating coil. This hardware bypass is exactly what prevents false trips, without relying on any software compensation at all.
But this physical mechanism is exactly why I have to deliver a pretty stark warning here. Never, ever apply high-impedance ref to mismatched CT ratios. Don't even try it just to see if it works, unless you really enjoy filling out extensive incident reports. If you mix a high-impedance scheme with severely mismatched equipment, say a 2,000 to 1 phase CT with a 1,000 to 1 neutral CT, that massive mismatch current during an external fault has nowhere to safely go but straight through the relay. You're risking false trips, or even worse, completely frying your protective components.
Let's move to a practical, real-world application tip. What if you're retrofitting a brownfield site? You know, in older sites, legacy CTs are often mismatched, or their ratios might even be a total mystery until you get deep into the project. In these scenarios, always default to low impedance REF. It is literally and figuratively the path of least resistance. The software-driven numerical compensation of LREF PNDF makes it highly adaptable to the messy, imperfect realities of existing infrastructure.
All right, let's pause for a quick scenario check to make sure this is all locked in. Imagine you're designing a protection scheme right now. You check your equipment and find your phase CTs are rated 1500 to 5 and your neutral CTs are rated 1000 to 5. Based on everything we've just covered, which ground fault scheme must you use? I'll give you just a second to think about it. The answer is, of course, LRFNDF, the low impedance numerical scheme. Because the turns ratios are different, the high impedance option is instantly eliminated, regardless of what you might prefer. A ratio mismatch leaves you with exactly one safe, functional engineering path, and that is, for sure, low impedance. Which brings us to a really common misconception in the industry. True or false, high impedance REF is always the superior choice because it's considered traditional and ultra-stable. I mean, engineers naturally love stability, so it's incredibly easy to assume the old-school hardware method is always better, right? Actually, false. High-impedance RFAP is only viable when CT ratios match perfectly and you're okay with external hardware. If your hardware constraints make high impedance impossible, using low-impedance LRFAP NDF is absolutely not a compromise. It is a powerful, flexible, and robust numerical solution that offers incredible reliability. Honestly, it's the correct and often the only workable choice for modern, complex, or retrofitted grids.
So the absolutely crucial takeaway here is that by properly applying either low or high impedance ref, you've successfully deployed that dedicated close-up camera. You have secured the blind spot near the neutral point where standard differential protection struggles. But this raises a massive operational question. You now have differential protection watching the phases and ground fault protection watching the neutral. How do you ensure all these separate protection stages communicate perfectly and fire the exact right breakers at the exact right millisecond when a fault actually happens? Well, that requires a flawless master trip logic, and that is exactly what we're going to be decoding in our next explainer. Catch you then.